In the winter of 1950, a Dutch astronomer named Jan Oort sat at his desk in the city of Leiden. Outside, a soft snow was falling over the canals. Inside, he was performing a piece of deduction that would redraw the map of the solar system. Oort was studying comets. Not the short and predictable kind, the ones that return every few decades like Halley or Encke, but the other kind, the long ones, the strange ones, the comets that appear in our skies after centuries or millennia of absence, burning bright for a few weeks, then retreating into the darkness for another unimaginable span of time. Where, Oort wondered, did these long-period comets come from? Where did they live in the quiet years between their visits?
And why did they arrive from every direction, not just from the plane of the planets, but from above and below, and from every angle in the sky? The answer, when it came to him, had the elegance of a proof that could not be any other way. If the comets arrived from all directions, their home must be spherical. It must surround the sun completely, like a shell around a lantern. And if their orbital periods were measured in tens of thousands of years, their home must be enormously distant, far beyond anything yet discovered. Oort calculated. He worked with pencil and paper, and with tables of orbital elements gathered by astronomers from the previous 2 centuries.
He noted the aphelia, the farthest points from the sun, where these comets lingered the longest. He found that many of them drifted out to distances of 50,000 astronomical units, 50,000 times the distance from the Earth to the sun. A distance so vast that light itself, the fastest thing in the universe, would take nearly a full year to cross it. And he proposed in a paper published that same year that there existed a reservoir of comets at that distance, a cloud, a shell, a vast population of frozen bodies hibernating in the darkness, occasionally perturbed by the gravity of a passing star and sent falling inward toward the light. He did not see it. He could not see it.
No telescope on Earth could resolve a comet-sized object at 50,000 astronomical units. The individual bodies were too small, too cold, too far. They emitted no light of their own, and the sunlight that reached them was diluted to the faintness of moonlight diluted across a continent. But he had inferred it. He had reasoned it into existence. And in the decades that followed, as more long-period comets were discovered and their orbits computed with greater precision, the evidence for this distant shell grew stronger and stronger. Every new comet, falling in from the dark, told the same story. There was something out there, a cradle of ice, a library of frozen primordial matter. Today, we call it the Oort Cloud, in his honor.
But Oort himself was not the first to imagine it. A few years earlier, the Estonian astronomer Ernst Öpik had proposed a similar idea, and so in some textbooks, you will see the name Oort Cloud. It is a small tribute to the way that science rarely belongs to one mind alone. Ideas drift, like comets, between the minds that receive them. And sometimes, when the conditions are right, they become visible. But Oort's calculation went further. He did not just say that the cloud existed, he estimated how many bodies it contained. He computed the rate at which comets fall inward, and from that rate, he extrapolated backward.
If so many comets visit the inner solar system each century, he reasoned, and if most of them are never seen a second time, then the total reservoir must be staggeringly large. trillions of bodies. A quiet city of ice, hanging in the outer dark. Imagine him there, in that Dutch winter of 1950, the war only 5 years behind him, Europe still rebuilding itself. And yet here he was, sitting at his desk, extending the boundary of the known solar system outward by a factor of 1,000, redrawing our home, expanding the house we live in, from the snug little family of planets to a sphere so vast it takes light a year to cross. There is something tender about this kind of science, something deeply human.
A man sitting alone in a quiet room, thinking about where comets go to sleep, and finding in his thoughts a new layer of the universe. He would live another 42 years after publishing that paper. He would see the space age begin, and the moon landed upon, and the Voyagers launched toward the outer planets. He would see confirmation of his hypothesis grow stronger with each passing decade. But he would not live to see any image of his cloud, and neither, in all likelihood, will any of us. The Oort Cloud is not a thing we can photograph. It is a thing we must infer. A thing we must imagine, carefully, through the mathematics of falling orbits and the statistics of comet arrivals.
It is, in a sense, the most abstract landscape in the solar system. The one we know about most completely through reason, and least through sight. And that, perhaps, is why it suits the night, why it suits this hour. Because the Oort Cloud is not a place we visit with our eyes. It is a place we visit with our minds, a place we drift into as we close our eyes and let the day dissolve. So come with me now. Close your eyes, or keep them open softly, and let us go outward together, past the familiar worlds, into the shell that Oort reasoned into being. It is worth pausing for a moment to appreciate the quality of the reasoning itself.
Because Oort's method was not unusual in astronomy, it was, in many ways, the classical method of the entire discipline. The planets themselves were first mapped through this method. Neptune was first predicted through the observed perturbations of Uranus, before any telescope was pointed to its position. The existence of dark matter was first inferred from the rotation curves of galaxies, long before any direct detection attempt. Black holes were first predicted from the mathematics of general relativity, decades before any were observed. Astronomy, perhaps more than any other science, lives and breathes in this space between what is seen and what must be inferred. The Oort Cloud belongs firmly in that tradition. It is a structure that exists, almost entirely, at the level of implication.
And yet, when you study the evidence, when you look at the distribution of comet orbits, when you model the gravitational dynamics of the outer system, when you compute the rate at which stellar encounters should occur, the Oort Cloud is not a speculation. It is a conclusion. It is a thing that must exist, given what we see. The alternative, that comets simply appear from nothing, that they manifest out of the interstellar medium without any reservoir, is far less plausible than the hypothesis of a vast spherical cloud of ancient bodies. And so, even without images, even without direct detection, the Oort Cloud stands on solid ground. It is as real, in the scientific sense, as the core of the Earth.
We have not seen the core of the Earth either. We have inferred it from seismic waves, from density calculations, from the magnetic field. The Oort Cloud, in a similar way, is inferred from the behavior of comets, from the dynamics of the outer system, from the statistics of orbital perturbations. There is a certain humility required in accepting this. An intellectual humility that says, yes, I believe in things I cannot see, provided the evidence is strong enough. This is not faith in the religious sense. This is a kind of epistemological courage, the willingness to let the mathematics carry you to places your eyes cannot follow. And the Oort Cloud is, among other things, a triumph of that willingness.
To understand the Oort Cloud, we must first pass through its nearer cousin, because the outer solar system is not one region, but two, and they are often confused, even by people who love the sky. Beyond the orbit of Neptune, at a distance of roughly 30 astronomical units from the Sun, begins a flattened ring of icy bodies called the Kuiper Belt. It extends outward to about 50 astronomical units. It lies roughly in the same plane as the planets. It contains Pluto. It contains Eris and Makemake and Haumea and the other dwarf planets that were once simply called the distant worlds. And it contains many thousands, perhaps millions, of smaller bodies. Trans-Neptunian objects, cold, dark, slow.
The Kuiper Belt is, in a way, the outer attic of the planetary system, the place where the leftover construction material from the formation of the planets drifted, cooled, and stayed. Its existence was predicted by the astronomer Gerard Kuiper in 1951, though Kuiper himself believed it had been cleared out by Pluto. It was the Irish astronomer Kenneth Edgeworth who had, a few years earlier, proposed that such a belt might still be populated. And so you will sometimes see the region called the Edgeworth-Kuiper Belt. The first Kuiper Belt object beyond Pluto was not discovered until 1992, a small world designated 1992 QB1. Since then, we have found thousands, and with each discovery, our map of the outer system has grown richer and stranger.
But the Kuiper Belt is not the Oort Cloud. They are profoundly different. The Kuiper Belt is flat. It lies in the ecliptic, the plane where the planets orbit. It extends only to about 50 astronomical units, which is still within the heliosphere, still within the region shaped by the sun's solar wind. Its bodies, though cold, are bathed in feeble but measurable sunlight. We can see them through our telescopes. We can photograph them. We have even, with the New Horizons spacecraft, flown past one and imaged its surface. The Oort Cloud, by contrast, is spherical. It surrounds the sun in every direction. It begins at thousands of astronomical units and extends outward to perhaps 100,000. It lies beyond the heliosphere, in the true interstellar medium.
Its bodies are effectively lost to observation. None have ever been directly imaged in situ. We know them only when one falls inward, warmed by approaching sunlight, and becomes a comet in our skies. So the two regions are cousins in substance, but strangers in geometry. The Kuiper Belt is a disk. The Oort Cloud is a shell. The Kuiper Belt gives us short-period comets, the ones that return every few decades because their orbits remain within the outer planets. The Oort Cloud gives us long-period comets, the ones that visit once every tens of thousands of years, or sometimes only once in all of recorded history.
There is a comet called C2020F3, also known as Neo-Wise, that graced our northern skies in the summer of 2020. Its orbital period was calculated at roughly 6,800 years. The last time it came close to the sun, the pyramids of Egypt were still new. Before that, it had drifted for millennia in the outer cold, a silent body in the Oort Cloud, unaware of the warmth it had once known. When it returned, it passed within our view for only a few weeks. Human eyes watched it. Phones were lifted to photograph it.
Children, in some households, were taken into backyards and shown a pale smudge in the northern sky, and told that this is a thing that travels on scales far beyond a human life. And then it was gone, back into the dark, back into the cloud. We will not see it again until nearly the year 9000 in the Common Era, by which time this civilization and everything we now call modern will be a distant memory, or perhaps less. This is the time scale of the Oort Cloud. This is its rhythm. Each of its inhabitants is a pendulum, swinging on an arc of 10,000 years, or 50,000, or 100,000. And when one of them passes through our sky, we see it only for a moment, like a face lit by a candle, before the candle is covered and the darkness returns. The Kuiper Belt, by contrast, is more domestic. Its bodies return on schedules we can almost live within. Halley's Comet, which is technically a short-period comet related to the Kuiper region, returns every 75 years. A long human life can see it twice. There is a warmth in that, a sense of family. The Oort Cloud is not family. It is ancestry. It is the deep past, still falling inward, still touching us, from a time we can only approach through mathematics. And to understand how it is structured, we must go further still.
Because the Oort Cloud itself is not one region. It is two. Before we move onward, though, there is a detail worth holding on to. The Kuiper Belt, for all that it is smaller and closer than the Oort Cloud, is itself a remarkable place. It is the largest structure in the solar system that is populated by discrete bodies. It contains, by some estimates, 100,000 bodies larger than 100 kilometers across. It is the source of all the short-period comets that visit our sky. And its most famous inhabitant, Pluto, has given us, through the New Horizons flyby of 2015, a surface more varied and beautiful than anyone had dared to hope. There are mountains of water ice on Pluto. There are plains of nitrogen ice.
There are glaciers and fractures and colors that shift from deep red to pale blue. It is a miniature, complete world, and it lies at only 40 astronomical units from the sun, a mere backyard compared to where we are going. The Kuiper Belt, in a way, is our bridge, a region we can reach, a region we can observe, a region from which we have returned images and data. The Oort Cloud, by contrast, is the far country, the place beyond the bridge, and even Pluto, which once seemed so remote, is in truth quite close to home.
If you scale the distance from the sun to the Oort Cloud's outer edge to the length of an American football field, Pluto would be sitting about 15 centimeters from the starting line. The entire known solar system, the entire domain of the 8 planets, and the Kuiper Belt would occupy only the first few steps of the field. The remaining 90+ meters would be the Oort Cloud. That is the shift in perspective that awaits us. A shift from the known, the mapped, the photographed, to the vast, the dim, the inferred.
Astronomers today speak of the Oort Cloud as having 2 parts: an inner cloud, closer to the sun, and an outer cloud, reaching toward the interstellar void. They have different shapes, different populations, different histories. And the boundary between them is not a line drawn on a map, but a gradual shift in character, a fading of one region into another. The inner Oort Cloud is sometimes called the Hills Cloud, after the American astronomer Jack Hills, who proposed its existence in 1981. It begins, by most estimates, at around 2,000 astronomical units from the Sun. That is 50 times farther than Neptune.
Its bodies are more tightly bound to the sun, held by gravity into orbits that, while enormous, are still firmly anchored. It is believed to be flatter than the outer cloud, more disk-like, a sort of puffed extension of the planetary plane, though much thicker than the Kuiper Belt. The outer Oort Cloud begins where the inner one fades, at perhaps 20,000 astronomical units, and extends outward to 100,000 astronomical units, or, in some estimates, even farther. 100,000 astronomical units is about 1.6 light-years. That is nearly 40% of the distance to the nearest star. Let that settle. The outermost reaches of our own solar system, by some measures, extend nearly halfway to Alpha Centauri.
The idea that we live inside a neat little system of planets, tidy and bounded, is a story we tell ourselves because the planets are bright. The truth is that our home is enormous, and most of it is empty, and most of its mass in terms of the number of objects is in this vast frozen periphery. The outer Oort Cloud is thought to be spherical, a true shell. Its bodies are only loosely bound to the sun. Their orbits take them so far from our star that even small perturbations, from the gravity of passing stars or from the combined pull of the Milky Way itself, can alter their paths. They are, in a sense, the most vulnerable citizens of our system.
The ones most likely to be kicked inward by a cosmic nudge, or kicked outward, free of the sun altogether, into the interstellar medium. And this is where the Oort Cloud becomes philosophically strange, because the outer cloud is not entirely ours. It is leaky. It loses members to space. It may gain members from space when the solar system drifts through clouds of interstellar debris. It is a population that trades, slowly, with the galaxy around it. The inner cloud is more stable, more like a vault. The Hills Cloud is thought to be a reservoir, a deep source, which can replenish the outer cloud when it loses bodies.
In this model, the outer cloud is a thin shell of escaping members, and the inner cloud is the mother population, quietly feeding the border. And beneath it all, these bodies are cold, profoundly cold. At 100,000 astronomical units, the Sun appears as little more than a bright star. Its light spread across that enormous sphere warms nothing. The temperature of an Oort cloud body is thought to hover near 4 degrees above absolute zero. That is colder than liquid helium, colder than any place in the inner solar system, colder than anywhere on Neptune or Pluto, or the surface of the most distant Kuiper Belt object we have imaged. At such temperatures, ices that we do not normally think of as ices become stones. Nitrogen freezes solid.
Oxygen freezes solid. Methane, carbon monoxide, carbon dioxide, all sit in crystalline forms harder than granite. An Oort cloud body is not a dirty snowball in the casual sense. It is a compound mineral, a mixture of frozen gases and rocky dust, welded together in a cold so intense that its chemistry has been essentially paused for 4.5 billion years. When one of them falls inward, and the sun's heat begins to warm it, we are, in a sense, reheating a fossil. The volatile compounds that outgas from a long-period comet as it approaches the sun are the same compounds that existed in the original solar nebula. The tale of a fresh Oort cloud comet is a breath from the birth of our world. We are, when we observe such a comet, looking at the ancient breath of our own origin. This is why astronomers care so deeply about these bodies. They are time capsules, perfect ones, unaltered by heating, unaltered by collisions, unaltered by the geological churning that has long since erased the early chemistry of Earth. To study a fresh Oort cloud comet is to read a letter written in the first few million years of the solar system, a letter that has lain unopened in the deepest cold for more than 4 billion years. And so, in the outer shell, we have a library, trillions of manuscripts, each one frozen at the moment of its writing.
Each one waiting, silently, for the rare perturbation that sends it falling inward, past Neptune, past Jupiter, past Mars, into the heat, where it unpacks itself into our skies, tells its ancient story in gas and dust, and then, perhaps returns to the dark. Consider, for a moment, the chemistry of these ancient bodies. The volatile ices they contain are not a single substance, but a layered assemblage of molecular species, each with its own freezing point, its own response to solar warmth. When a long-period comet approaches the sun, the different ices sublimate at different distances. Water ice, the dominant volatile by mass, begins to produce significant gas only when the comet approaches within 3 or 4 astronomical units. Carbon dioxide sublimates earlier, at around 10 astronomical units.
Carbon monoxide, one of the most volatile species, can begin outgassing at distances beyond 20 astronomical units. Each comet, as it falls inward, reveals its composition in stages, like a long biography told in chapters. This is why comet spectroscopy is so exciting. By observing the gases released at different distances from the sun, astronomers can infer the layered structure of the cometary nucleus. They can determine, with reasonable precision, the relative abundances of different ices. They can detect unusual signatures. They can trace, within a single comet, the chemical history of the region in the early solar nebula where the comet was originally assembled. And here, something remarkable begins to emerge. Many long-period comets show unusual enrichments of certain molecular species.
high abundances of molecular nitrogen.
Isotopic ratios of hydrogen and oxygen that are distinctive and fingerprint-like. These chemical signatures are like labels. Labels that tell us where, roughly, in the primordial solar nebula, each comet was born. Some appear to have formed in the giant planet region. Others may have formed even closer to the Sun. A few show signatures that hint at formation in the very outermost regions of the disk, beyond where Neptune now orbits. The Oort Cloud, then, is not chemically uniform. It is a mixed population. Different bodies from different birthplaces, all flung outward by the gravity of the early planets, all now drifting together in the same vast shell. A community of exiles from different neighborhoods of the same ancient city.
A cosmopolitan population, if you will, united not by origin but by destination. And this is not just a curious detail. It tells us something profound. It tells us that the early solar system was a place of dynamical upheaval, that bodies were flung, rearranged, scattered, and redistributed over the course of hundreds of millions of years. That the present-day arrangement of the planets, the Kuiper Belt, and the Oort Cloud is the end result of a long period of chaos. The solar system we know is a solar system that has settled. The Oort Cloud is the memory of its unsettled youth.
How many bodies live in the Oort Cloud? The honest answer is that no one knows. But the estimates, based on the rate at which long-period comets arrive in the inner solar system, are staggering. Most modern calculations suggest that the total population is on the order of 1 trillion to 10 trillion bodies larger than 1 kilometer in diameter. That is 1,000 billion to 10,000 billion bodies. A cloud of ice chunks, each at least the size of a small mountain, spread across a sphere 100,000 astronomical units across. And that counts only the large ones. The cometary nuclei. The objects that would become visible if nudged inward.
If you include smaller bodies, down to the size of a small town, or a neighborhood, or a house, the count could be far higher still. Hundreds of trillions, perhaps even more. The total mass, however, is not as large as one might think. Each body is a speck. The individual comet nuclei are typically between 1 and 50 kilometers in diameter. Even if you sum up trillions of them, the total mass is modest. Most estimates place the combined mass of all Oort Cloud bodies at somewhere between 1 and 5 Earth masses. That is, the entire cloud, all trillion of its members, weighs about as much as our planet, perhaps a few planets. This is a strange reality.
A cloud that fills a sphere hundreds of thousands of astronomical units across. A cloud that surrounds us in every direction. A cloud containing more individual bodies than there are stars in our galaxy. And yet, its total mass is only a handful of Earths. It is a cloud made of almost nothing, a scattering so sparse that if you were to stand on the surface of one Oort Cloud body and look toward the next one, the nearest neighbor would be, on average, tens of millions of kilometers away. That is more than the distance from the Earth to Venus at their closest approach. Imagine standing on a rock in the dark and knowing that the next rock is farther from you than Venus is from Earth.
You would never see it. It would never see you. You would drift through your 10,000-year orbit entirely alone. This is the texture of the Oort Cloud. Not a crowded shell, not a busy highway of ice, but a profound, distributed loneliness. Each body swinging on its own silent arc, around a sun so distant that it provides no heat and barely provides light. Each body accompanied in its vast neighborhood by nothing visible, only the faint pull of a star that lit its sky from the moment of its creation and will continue to light its sky for as long as the star exists. And yet, despite this sparseness, the Oort Cloud is not empty in the mathematical sense. It is populated. It has structure.
It has an inner region and an outer region. It has streams and clumps and statistical features that astronomers have begun to model with ever greater detail. Some of the comets that fall inward appear to come in groups. Clusters of comets arriving from similar directions, sharing similar orbital parameters, as if they had been disturbed by the same ancient event. A passing star, perhaps, 10 million years ago, whose gravity combed through part of the outer cloud and sent a ripple of bodies falling inward, a ripple that still reaches us today. This is remarkable. Think about what it means.
The comet you see in the sky tonight, if it happens to be a long-period one, may be arriving because of a stellar encounter that took place before humans were even a species. The gravitational nudge that started it falling may have been applied when our ancestors were still primates, not yet walking upright. The Oort Cloud is a memory, a gravitational memory of events in the history of the galaxy, preserved in the delayed arrivals of comets in our sky. And the cloud's own origin is deep. It is believed that most of its bodies did not form where they now reside. They formed in the inner solar system, among the giant planets, during the first tens of millions of years of the system's history.
Jupiter, Saturn, Uranus, and Neptune, with their enormous gravity, flung vast quantities of small, icy bodies outward. Some of these bodies were flung so fast that they escaped the sun's gravity altogether, lost forever to the galaxy. But many were flung onto very high, very slow orbits, and rather than escaping, they simply drifted outward to distances of thousands or tens of thousands of astronomical units. Out there, in the quiet, their orbits were gradually smoothed by the gravity of passing stars and by the tide of the Milky Way itself. Over hundreds of millions of years, their orbital paths were randomized, their planes of motion scrambled, their perihelia lifted out of the region where the giant planets could still pull on them. And so they settled
into the spherical shell we now call the Oort Cloud. Not their birthplace, but their retirement home. This is why the Oort Cloud is so cold, so primordial, so full of the chemistry of the early solar nebula. Its bodies were processed briefly in the warm inner system, then flung out to the deep freeze, where they have remained unchanged for 4.5 billion years. They are, in a sense, our exiles, the wanderers we cast out when we were building the planets. And now occasionally, one of them returns, falling back through the system, briefly visiting the warm place where it once was born, before retreating again into the dark. 1 trillion exiles. 1 trillion memories. 1 trillion faint and frozen bodies, drifting in silence, waiting for a gravitational whisper, or perhaps waiting for nothing at all, simply existing, simply being there. A quiet population, mostly unseen, mostly unimaginable, at the outer edge of a world we thought we knew. There is another thought worth dwelling on here.
A thought about the nature of numbers. A trillion is a word we use, but it is not a quantity the human mind can truly grasp. If you tried to count to 1 trillion, one number per second, without stopping, without sleeping, without pausing, it would take you more than 30,000 years. If you had started counting at the dawn of agriculture, you would still be counting today.
If you had started counting when the pyramids were built, you would be only about 1/6 of the way through. 1 trillion is not a human number. And yet, in the Oort Cloud, we believe there are at least that many distinct icy bodies. Each of those bodies has its own history. Each was formed at a specific moment, in a specific region of the early solar nebula, out of specific grains of dust and specific molecules of ice. Each was flung outward by a specific gravitational encounter, or a series of them. Each now follows its own specific orbit, with its own specific period, its own specific inclination, its own specific perihelion. The Oort Cloud is not a homogeneous gas. It is a community of distinct individuals. Trillions of them, each one, in some sense, a protagonist of its own quiet story. And there is something oddly democratic about this picture. In the inner solar system, a handful of large bodies dominate. 8 planets, a few dwarf planets, the sun, the moon. The cast of characters is small, and we have named most of them, and we know their birthdays and their orbital periods and their weather patterns. We can practically list them. But in the Oort Cloud, the roster is unreadable. It is a phone book of 1 trillion entries, nearly all of them anonymous. It would take many lifetimes, at a rapid pace, simply to name them all. And we have named so far only a handful. Sedna, the Goblin, Laikuhonua, a few others.
The rest remain in anonymity, distinguished only by their individual orbits, each of which is its own signature, its own fingerprint, even if we cannot yet read it. This anonymity is not a failure of our telescopes. It is the nature of the cloud. Even with future instruments, we will detect only the largest, the closest, the brightest of the Oort Cloud's members. The vast majority will remain forever beyond our ability to resolve. They will exist, as the theorists say, in a statistical sense. We will know that they are there, in their trillions, but we will never speak their names. They will simply be out there, in the quiet part of the population, anonymous, patient, complete.
In the year 2003, on the night of November the 14th, an astronomer named Michael Brown, working at the Palomar Observatory in California, was examining a set of images taken the previous night. He was searching for distant bodies beyond Neptune, faint points of light that had moved, ever so slightly, between exposures. And he noticed one. It was very far away, very faint, very slow. And when he computed its orbit, the numbers made him stop and stare. The object, which would later be given the official designation 90,377, and the name Sedna, after the Inuit goddess of the sea, had an orbital period of roughly 11,400 years. Let that sit with you for a moment.
11,400 years. The last time Sedna was at the equivalent point in its orbit that it occupies today, no human civilization had yet built a city. Agriculture was just beginning. The glaciers of the last ice age were still retreating from Europe. No pyramid had been built. No word had been written. No wheel had been turned. And during all of that time, Sedna had been tracing the same slow, silent arc around the sun. Never stopping, never accelerating. Moving at a few hundred meters per second, which is fast by human standards, but glacial on the scale of its orbit.
If you had stood on Sedna's surface throughout the entirety of human history, you would have seen the sun remain essentially in the same part of your sky. A tiny, intense point, brighter than any star, but not bright enough to warm your skin or cast a visible shadow at your feet. Sedna is remarkable for another reason. Its closest approach to the sun, its perihelion, is at 76 astronomical units. That is well beyond the Kuiper belt, well beyond the gravitational reach of Neptune. And yet its farthest point, its aphelion, is at more than 900 astronomical units. This is an orbit unlike anything else known in the solar system. The puzzle is this.
If Sedna had been captured by one of the known giant planets, it would have perihelion within the region where those planets orbit. It would dip back toward Neptune occasionally, but it does not. Its perihelion is lifted, permanently, away from Neptune's influence, which means Sedna was placed on its current orbit by something else. Something the known solar system cannot explain. This is why Sedna is so important. It is not a normal Kuiper belt object. It is not a normal scattered disk object. It is a body that lives in a region between the Kuiper belt and the Oort Cloud, a region that many astronomers now call the inner Oort Cloud, or the Sedna region.
It is, in other words, the first confirmed inhabitant of the long-predicted Hills cloud. And it is strange, deeply strange. At its most distant point, Sedna is 900 astronomical units from the sun. From that distance, the sun would appear only about 20 times brighter than a full moon as seen from Earth. That may sound like a lot, but it is not. 20 times a full moon is still very dim. It would not cast a crisp shadow. It would not warm the ground. The sun at Sedna's aphelion is a bright needle in the sky, not a disk. The surface of Sedna is thought to be one of the reddest in the solar system.
Its color is attributed to long-chain organic compounds called tholins, which form when ices containing methane and nitrogen are bombarded by cosmic radiation over billions of years. Sedna has been out there, absorbing that radiation, weathering its surface into a deep crimson for longer than complex life has existed on Earth. Imagine it, a small, lonely, red world, about 1,000 kilometers in diameter, drifting through the dark at such a glacial pace that even a century of observation barely shifts it against the background stars. A world with no moons, no atmosphere, no weather. A world where the sun never warms anything.
A world whose orbit is so elongated that it spends most of its time drifting out near the Oort Cloud, and then, over thousands of years, falls inward, brushes through the inner system at its closest approach, and begins the long climb back out. Sedna was, in 2015 or so, near its closest approach to the sun. We are watching it now, in what is effectively the warmest part of its life. And yet it is still too cold for any meaningful chemistry, too dim for any direct imaging beyond a point of light, too remote for any probe we currently possess to reach it in any reasonable time. It will pass its perihelion, and then begin the slow outward climb. It will spend the next 11,000 years receding from us. By the year 13,000 of the Common Era, it will be back at its aphelion, 900 astronomical units away. Every human civilization that will ever exist, between now and then, will watch the same Sedna move incrementally through the same slow arc. There is a kind of dignity in this, a kind of steadiness. Sedna is older than any monument, more patient than any ruler, more silent than any grave. It does not need to be remembered. It simply persists. It simply moves. A red body in the dark, following its orbit as if nothing else in the universe mattered, because from its perspective, perhaps nothing else does. But Sedna is not alone. Not quite.
Because in the years following its discovery, astronomers found other bodies like it. Objects with perihelia beyond Neptune's reach. Objects with enormous orbits. Objects that could not be explained by the known planets alone. And as the list of these extreme bodies grew, a pattern began to emerge. A pattern that would change our view of the outer solar system entirely. But before we turn to that pattern, let us stay with Sedna a little longer. Because Sedna is not merely an orbital curiosity. It is a world. A small, red, quiet world. And like every world in the solar system, it has a character of its own. Its diameter is estimated at roughly 1,000 kilometers.
That makes it somewhat smaller than Pluto, which is about 2,300 kilometers across, but similar in scale to other dwarf planets. Its surface gravity, if you could stand on it, would be about 1% of Earth's. You would weigh, in human terms, less than a kilogram. You could, in principle, jump high enough to escape the surface entirely, given sufficient speed. Though escaping Sedna's gravity is not the same as escaping Sedna's loneliness, and that no jump could free you from. Its day, the length of its rotation, is roughly 10 hours. That means, despite its languid, millennia-long orbit, Sedna itself spins quite quickly on its axis. A Sednan day lasts half of an Earth day.
If you were to stand on its surface, you would see the distant sun rise and set twice in every 24 hours of Earth time. It would be a strange rhythm, short days, impossibly long years. And its sky, that is the hardest part to imagine, and perhaps the most beautiful. At Sedna's distance, the sun is a pinprick, brighter than all other stars combined, yes, but still essentially a point. There are no recognizable constellations from Sedna that look different from those we see on Earth, because the distance to the nearby stars is still vastly greater than the distance from Sedna to the sun.
The Milky Way, stretching across the Sednan sky, would look almost identical to how we see it, except that the sun would be just another bright point in its crowd. Imagine standing on a small, cold, red rock, looking up and trying to pick out which of the many bright stars is your star, the one that made you, the one that defines your orbit, the one that, for 11,400 years at a stretch, is the quiet center of your existence. That is the sky of Sedna, a sky where home is just another point of light.
9 years after Sedna was discovered, in the year 2012, a second body was found with an orbit remarkably similar in shape. Its designation is 2012 VP113. The digits sound clinical, but the object itself is anything but. It is a small world, perhaps 450 kilometers across, with a perihelion at 80 astronomical units and an aphelion at more than 450 astronomical units. Like Sedna, it lives beyond the reach of Neptune. Like Sedna, its perihelion cannot have been placed there by any known planet. And like Sedna, it takes thousands of years to complete a single orbit. Astronomers began to call these objects the extreme trans-Neptunian objects, the extremes, the outliers.
A family of bodies that seem to inhabit the inner Oort cloud. Each one a different size, a different color, a different history, but all sharing the same strange orbital characteristic. Perihelia lifted far above Neptune. Aphelia reaching out toward the true deep dark. In the years that followed, more were found. There is 2014 SR349 and 2013 FT28 and 2015 TG387 and a handful of others. Each one was detected after careful photographic searches by astronomers who knew by then what they were looking for. And then, in 2018, came the discovery of an object with the delightful
A but small world with a perihelion at 65 astronomical units and an aphelion at more than 2,000 astronomical units. It takes 40,000 years to complete a single orbit. 40,000. The goblin was born before modern humans had painted on cave walls, and it is still out there, still moving, still tracing its arc. And then, in 2020, came Lelia Kuhonua. 2018, AGS 37. Its name comes from a Hawaiian creation chant, and it means, roughly, the one who embodies the border of the sky. An exquisite name for an object with an aphelion of more than 2,100 astronomical units and an orbital period of more than 30,000 years. Lelia Kuhonua is one of the most extreme of the extremes.
Its orbit takes it so far from the sun that for most of its journey, the sun is merely a bright star, and the stars of the Milky Way are all that light its sky. These bodies, Sedna and VP 113, and the Goblin and Lilikuhonua and their siblings, together form a small but remarkable sample, a handful of known inhabitants of the inner Oort Cloud, a census of the shell that Oort reasoned into being 70 years earlier from the arrivals of long-period comets. And here is the strangest part. When astronomers plotted the orbits of these extreme objects, they noticed something. The orbits were not random. They seemed to cluster.
their longest axis, the lines connecting their closest and farthest points from the sun, pointed in similar directions. Their angles of inclination relative to the plane of the planets were tilted in similar ways. Their arguments of perihelion, the angle at which they swing closest to the sun, were grouped. This clustering, if real, and not a statistical illusion born of small sample size, begs for an explanation. Because random orbits do not cluster, something must be aligning them. Something must be gently shepherding them into a shared pattern. There are a few possibilities, One is that the clustering is an artifact of observation, that we simply have not looked in enough directions and have therefore produced a biased sample. Another is that the clustering is real, but is the lingering imprint of some past event, like a star passing close to the solar system long ago, or a piece of a now destroyed object whose gravity briefly shepherded these bodies. But there is a third possibility, one that has, since 2016, captured the imagination of astronomers and the public alike. A possibility that, if true, would mean that our solar system contains a planet we have never seen. A planet that shapes the orbits of these distant bodies through its gravity. A planet that lives, perhaps, deep in the inner Oort Cloud itself. A planet that we have come to call, for lack of a better name, Planet 9.
The idea of a hidden planet in our solar system is not new. It has, in fact, a long and colorful history. In the late 1800s and early 1900s, several astronomers suspected the existence of a planet beyond Neptune based on apparent anomalies in the orbits of Uranus and Neptune. This hypothetical world was called Planet X. The search for Planet X, in fact, led directly to Clyde Tombaugh's discovery of Pluto in 1930. At the time, Pluto was hailed as the long-sought Planet X. Later analysis, however, showed that Pluto was far too small to account for the supposed anomalies. And later still, more precise measurements of Neptune's orbit revealed that there were no anomalies to explain. Planet X, in that earlier sense, did not exist.
Pluto was simply a small, cold world in the Kuiper Belt, discovered somewhat serendipitously during a search for something else. So when Beidigen and Brown proposed Planet 9 in 2016, they did so with full awareness of the history. They did so knowing that hidden planets in the outer solar system had been proposed before and had not panned out. They did so knowing that the history of astronomy is littered with hypothetical planets that were later ruled out. Vulcan once thought to orbit inside Mercury's orbit. Nemesis once thought to be a dim companion to the Sun causing periodic extinction events. Each of these had its moment of plausibility, and each was eventually dismissed.
The question for Planet 9 is whether it will follow the same fate as Vulcan and Nemesis, or whether it will follow the fate of Neptune, which was predicted from perturbations, and then successfully found where it had been predicted to be. Time will tell. But the evidence at the moment is stronger than for most of the historical failures. The clustering is real by most statistical measures. The required planet mass and orbit are physically reasonable. The search is ongoing with instruments capable of finding it. The next few years are likely to be decisive. On the 20th of January, 2016, two astronomers at the California Institute of Technology published a paper that sent ripples through the scientific community. Their names were Konstantin Batygin and Michael Brown. The same Michael Brown who had discovered Sedna 13 years earlier, and the same Michael Brown who had, in 2006, been at the heart of the effort that led to Pluto's reclassification as a dwarf planet. The paper was titled, with characteristic understatement, Evidence for a Distant Giant Planet in the Solar System. And its argument was this: the observed clustering of the extreme trans-Neptunian objects, Sedna and her siblings, cannot be easily explained by chance. It cannot be easily explained by any known object.
But it can be explained, quite precisely, if there exists a ninth planet in the outer solar system, with a mass of roughly 5 to 10 Earth masses, on a highly elliptical orbit, with a semi-major axis of perhaps 400 to 800 astronomical units. In other words, a world larger than Earth, perhaps larger than Uranus or Neptune in diameter, but drifting at distances 10 times greater than Neptune's orbit. A world that takes, by some estimates, 20,000 years to complete a single circuit around the Sun. If it exists, Planet 9 would be the first new major planet in our solar system discovered since Neptune was found in 1846. It would be a tremendous scientific event, a rewriting of the solar system's inventory.
A new world, but the key word is if, because we have not yet seen it. The argument for Planet 9 is indirect. It rests on the clustering of orbits. It rests on statistical analyses that claim the clustering is very unlikely to be a coincidence. It rests on detailed dynamical simulations that show that a planet of the right mass on the right orbit would produce exactly the kind of clustering we see. These arguments are strong. Many astronomers find them compelling. Beitigen and Brown, and the scientists who have built on their work, have continued to refine their predictions. They have narrowed down the likely location of the planet to a specific region of the sky. They have predicted what its brightness should be.
They have estimated its possible temperatures and surface properties. They have been searching for it, tirelessly, with the largest telescopes in the world. And yet, as of this moment, no image of Planet 9 has ever been confirmed. No one has ever definitively pointed a telescope at a spot of sky and said, "There, that is it. That is the 9th planet." The search continues. The skepticism continues. The hypothesis remains unresolved. Why is it so hard to find? There are several reasons, and each of them tells you something about the depth and difficulty of the outer solar system. First, the predicted location of Planet 9 is not precisely known. The clustering analysis suggests a general region of sky, but a region covering hundreds of square degrees.
That is an enormous area to search at the depth required. Second, if Planet 9 is at 400 or more astronomical units from the Sun, it is extremely faint. Its surface would receive only a tiny fraction of a percent of the sunlight that Earth receives. The light that reflects off of it must then travel back across that enormous distance to reach us. By the time it arrives, it is vanishingly dim. Most modern estimates place Planet 9's apparent magnitude somewhere between 22 and 25. That is far fainter than anything visible to the naked eye, and fainter than most telescopes can easily detect across a wide field of view. Third, Planet 9 moves very slowly against the background stars.
At such a great distance from the Sun, its motion is so small that you need to compare images taken months or years apart to detect any shift. And because many asteroids and trans-Neptunian objects appear at similar apparent magnitudes, the task of distinguishing a potential Planet 9 from the noise of known minor bodies is formidable. Fourth, and this is the most poetic reason, there are parts of the predicted search region that pass through the plane of the Milky Way. In those regions, the background is crowded with stars. A faint dot of light that is actually a planet in our solar system is indistinguishable, in a single image, from the thousands of distant stars clustered behind it. The Milky Way becomes a veil.
A beautiful, glittering veil that could hide a world, and so astronomers keep looking. They use the Subaru telescope in Hawaii. They use the dark energy camera in Chile. They will soon use the new Vera C. Rubin Observatory, whose wide-field surveys are expected to begin yielding data any year now. If Planet 9 exists,
And if its properties are close to what Batygin and Brown have predicted, the Rubin Observatory should have a very good chance of finding it within the next few years. Or not. That is the tension. That is the drama. The next few years may bring a moment that goes into every textbook ever written about astronomy.
The announcement of a confirmed ninth planet, the first new major body in our solar system in more than a century and a half. Or, alternatively, the next few years may bring a more careful analysis that shows the clustering was a statistical accident, or that the hypothetical planet does not have the properties required, or that the search has simply failed to find anything. Either outcome would be meaningful. A confirmed Planet 9 would mean our solar system has a hidden giant, a planetary shepherd of the inner Oort Cloud, a world shaping the orbits of the distant ice bodies through its gravity.
A ruled-out Planet 9 would mean we must look for other explanations for the clustering, and we may be forced to accept that we do not yet fully understand the dynamics of the outer system. Both possibilities, in their own way, are beautiful, because both admit the same underlying truth, that our solar system is larger, stranger, and more mysterious than we have yet understood, that there are, in the deep dark, still things we have not found, still questions we have not answered, still worlds that might be waiting to reveal themselves, or not, to be replaced by stranger questions still.
Let us pause for a moment and imagine. Let us indulge the possibility. Let us assume that Planet 9 is real, and that it is roughly what Batygin and Brown have suggested. What kind of world would it be? Its mass, by current estimates, would be between 5 and 10 Earth masses. That places it firmly in the category of planets called super-Earths, or mini-Neptunes, a category that is common in the galaxy at large, around other stars, but which has, until now, been conspicuously absent from our own system. Our solar system has a cluster of small, rocky planets in the inner region, and a cluster of giant gas and ice planets in the outer region. But we have no intermediate case.
No world of 6 or 7 Earth masses. Planet 9, if it exists, would fill that gap. Its composition is uncertain. At that mass range, and at that distance from the Sun, it could be a rocky super-Earth with a thick hydrogen envelope. It could be a small Neptune-like ice giant with a water-rich interior and a thick atmosphere. It could be something else entirely, a composition we have not yet seen in any known planet. Its temperature would be extraordinarily low. At 400 astronomical units, the equilibrium temperature of Planet 9 would be perhaps 40 or 50 Kelvin. That is negative 220 Celsius. Colder than the surface of Pluto. Colder than almost anywhere in the solar system except the deep interiors of the Oort Cloud itself.
Its atmosphere, if it has one, would be a frozen mist of hydrogen and helium, with traces of methane and perhaps water ice floating as fine crystals. Its orbital period would be somewhere between 10,000 and 20,000 years. Let that wash over you. A single year on Planet 9 is longer than all of human history. When Planet 9 was last at its closest approach to the Sun, assuming a roughly 15,000-year orbital period, our ancestors were painting bison on the walls of caves. When it next reaches perihelion, whatever descends from us, if anything, will live in a world entirely unimaginable to us now. Its orbit is highly elliptical. The planet's distance from the Sun would vary enormously during its year.
At its closest approach, perhaps 200 to 300 astronomical units. At its farthest, perhaps 800 to 1600 astronomical units. For most of its long year, it would be very far away, drifting slowly through the cold. For a relatively short fraction of its year, perhaps 1,000 years or so, it would be closer to the Sun, though still more than 6 times as far as Neptune. Its orbital plane is probably tilted, not aligned with the plane of the 8 known planets, but tilted by perhaps 15 to 30 degrees. This makes it even harder to find, because astronomers cannot simply search along the familiar ecliptic. They must search regions of sky that are, in cosmic terms, off the beaten path.
And if it has moons or rings or any of the ornamental features that the other giant planets possess, we do not yet know. We cannot resolve any such features. At its distance, Planet 9, if it exists, is at best a single point of light. No disk, no detail, no discernible structure, just a dot moving very slightly between images taken months apart. This is what it would mean to find it, not a photograph of a gas giant with bands and storms, not a new Jupiter, full of visual splendor, but a faint star-like dot, moving slowly in a patch of sky where no moving object should be. A dot that, when its orbit was computed, would reveal itself to be gravitationally bound to our Sun.
A dot that would, over the following years and decades, be studied with ever larger telescopes, and eventually, perhaps, imaged with the direct imaging capabilities of future space observatories. A quiet discovery, in a way. Not a moment of spectacle. A moment of mathematics. A slow confirmation that what had been inferred was in fact there. The implications, however, would be profound. A Planet 9 discovery would expand our solar system's planetary inventory by 12%. It would place a super-Earth, for the first time, within our local knowledge. It would provide a natural explanation for the clustering of the extreme trans-Neptunian objects. It would demonstrate powerfully that the outer solar system is not empty, that it contains more than just frozen cometary nuclei, that it contains at least one hidden giant.
And it would open up new questions. Where did Planet 9 come from? Did it form in place at hundreds of astronomical units, which seems dynamically very difficult? Did it form closer in, perhaps in the region of the giant planets, and then get flung outward by a gravitational encounter early in the solar system's history? Did it start its life as a planet of another star altogether, captured by our Sun during a close encounter in the distant past, and therefore representing a genuine exoplanet that now lives within our system? Each of these scenarios is dynamically possible. Each of them would have different implications for our understanding of planet formation. Each of them would open new chapters in the textbooks.
And there is a quieter implication, one that the science rarely addresses directly, but that I think is worth noting. The discovery of Planet 9 would mean that there is, among us, a world we did not know, a world we have not touched, a world we have no photograph of, a world that has been with us, shaping our solar system for 4.5 billion years, and that we have been unaware of for all of human history. That is a humbling thought, that we have been living inside a solar system with a hidden giant, and have only now, in the last decade, begun to infer its presence. It tells us something about how much we still do not know.
about how much of our own home remains unmapped, about how even our local neighborhood, the place we call the sun and its planets, is still in many ways a mystery. And if Planet 9 is not there, if the search concludes that it does not exist, that too would be a kind of lesson. Because the clustering of the extreme trans-Neptunian objects is still a puzzle, and the puzzle would then force us towards stranger explanations. A galactic tide more influential than we thought, a swarm of smaller bodies combining their gravitational influence, an ancient stellar flyby that left its imprint. Any of these explanations, if correct, would enrich our understanding in different ways. Either way, the outer solar system is whispering to us.
And we have only just begun to listen. How do you find a world that does not want to be found? How do you search the dark for a planet that you can barely detect, in a sky full of noise, in a region full of confusion? How do you look for something that, by its very nature, hides? The search for Planet 9 and for other hidden bodies in the outer solar system has become one of the most compelling campaigns in modern astronomy. It involves a suite of observational strategies, each with its own strengths and weaknesses. The first and most obvious approach is wide-field optical imaging. You take large telescopes with wide fields of view and you photograph big swaths of the sky again and again, months apart.
You then compare the images, looking for any point of light that has moved. The moving points are candidates. They could be asteroids, Kuiper Belt objects, nearby stars, or, in the rarest case, a previously unknown planet. This is the classical method. It is the same basic method used by Clyde Tombaugh when he discovered Pluto in 1930. It is the method used to discover Sedna and her sisters. It is the method used by every modern survey, from the Palomar Distant Solar System Survey to the Dark Energy Survey to the upcoming Rubin Observatory. But it has limitations. At Planet 9's expected distance, the expected motion over a year is only a few arc-minutes. The expected brightness is at or below the magnitude limit of most surveys.
The expected position on the sky is within a very large search region, and the background in many parts of the search region is crowded with stars. So astronomers supplement the optical search with other approaches. One approach is to look for the infrared signature of Planet 9. Even if the planet is very dim in visible light, it might glow faintly in the infrared because it has some residual internal heat left over from its formation. A very cold planet still radiates, just at very long wavelengths. Infrared space telescopes, like the now retired WISE and the ongoing James Webb Space Telescope, have the potential to detect such a faint thermal signature if the planet is in the right place.
Another approach is to look for the effects of Planet 9 on other bodies. Not just the clustering of the extreme trans-Neptunian objects, but also, potentially, perturbations in the orbits of spacecraft in the outer solar system. The Pioneer probes, the Voyager probes, and the New Horizons probe all have their trajectories tracked with exquisite precision. If Planet 9 exists and has the predicted mass, it might, over the course of decades, introduce small deviations in these trajectories. Deviations so small that they are at the edge of detectability. Deviations that, if found, would be a powerful confirmation or refutation of the hypothesis. Another approach,
and this one is particularly elegant, involves the cosmic microwave background.
The cosmic microwave background is the faint afterglow of the Big Bang, a nearly uniform bath of microwave radiation that fills the universe. If Planet 9 exists, it is warm enough to emit a very small amount of microwave radiation itself, even in the absence of sunlight. And it would, in principle, stand out as a slight warm spot against the cold background of the microwave sky. Several teams have searched data from microwave telescopes, including the Planck satellite and the Atacama Cosmology Telescope, for exactly this kind of signal. So far, no confirmed detection has been made. But the searches continue, and more sensitive instruments are being built. And there is one more approach, still largely theoretical, but philosophically delightful. Gravitational waves.
If Planet 9 is a compact, dense object, and if it is moving with respect to other nearby masses, it might, in principle, emit a very tiny gravitational wave signal, detectable only by next-generation instruments. This is not a practical search method today, but it is a reminder that, as our instrumentation deepens, new channels of detection become possible. And so, from multiple directions, from multiple wavelengths, from multiple physical principles, astronomers converge on the hunt. They ask the sky, is there a planet there? They ask the microwave background, is there a warm spot? They ask the trans-Neptunian orbits, what shapes you this way? They ask the Voyager trajectories, what pulls you that way? They ask, and they ask again, and they wait for the sky to answer.
It is, in a sense, one of the most interesting detective stories in the history of science. An unseen suspect, a set of clues scattered across billions of kilometers of space, a team of investigators, armed with telescopes and mathematics and patience, slowly narrowing down the possibilities. Sometimes, clues are revised. Sometimes new evidence emerges. Sometimes, a lead goes cold, and the investigators must return to the drawing board. The Rubin Observatory, which is expected to begin its decade-long legacy survey of space and time any year now, will, many astronomers believe, either find Planet 9 or significantly constrain its non-existence within the first few years of its operation. It is a very exciting prospect.
We may, in our own lifetimes, see the announcement of a new planet, or the announcement that there is no such planet. Either way, we will learn. And in the meantime, we continue to drift. Through the vast shell of frozen bodies, through the quiet, through the cold, through the mystery. We continue to listen. We continue to look. We continue to ask. Because whether or not Planet 9 exists, the Oort Cloud is real. Sedna is real. Lelikuhonua is real. The shell of 1 trillion frozen bodies, drifting in silence at 100,000 astronomical units, is real. And whatever lives in its depths, known or unknown, is part of our system, part of our story, part of the sky.
There is one more search strategy worth mentioning, because it is philosophically lovely. It is the search for occultations. Occultation is the event in which a distant object passes in front of a star, briefly blocking its light. If an Oort cloud body, or Planet 9 itself, happened to pass directly in front of a background star, the star's light would dim slightly for a fraction of a second. With sensitive enough instruments monitoring millions of stars continuously, such events could be detected statistically. a sudden flicker, a momentary shadow, and from that flicker, the size, distance, and orbit of the occulting body could be inferred. Several research programs have pursued this strategy.
They have built arrays of small telescopes, each monitoring thousands of stars simultaneously, each looking for the brief dimming that would betray the passage of a distant body. So far, the statistics are consistent with the expected populations of the Kuiper Belt. The Oort Cloud, being more distant and more sparse, is much harder to catch through occultations. But the effort continues, and over the coming decades, as more telescopes come online, as more data is collected, as algorithms improve, the sensitivity will grow. Eventually, perhaps, we will catch a shadow, a single brief dimming, and from that shadow, we will extract the presence of a world no one has ever seen. It is a strange way to discover things, by catching their shadows.
By watching for the absence of light rather than its presence. But perhaps it is fitting, because the Oort Cloud, after all, is a place defined by absence. Absence of light, absence of warmth, absence of neighbors, absence of weather. It would be appropriate if its members were discovered one by one through the absences they momentarily cast across distant stars.
On the 5th of September 1977, from Cape Canaveral in Florida, a spacecraft was launched into a late summer sky. It was called Voyager One. It weighed less than 1,000 kilograms. It carried a payload of scientific instruments, a plutonium power source, and a golden record containing greetings from Earth in 55 languages, along with music and images meant to represent our civilization to any intelligence that might one day find it. Voyager 1's primary mission was to visit Jupiter and Saturn. It was to photograph those worlds, study their moons, measure their magnetic fields, listen to their radio emissions, and then, if everything went well, continue outward. And it did. It reached Jupiter in March of 1979.
It showed us the volcanoes of Io, the cracked ice of Europa, the titanic storms of the king of the planets. It photographed the red spot in color for the first time. It gave us a new Jupiter, richer and stranger than any previous one. It reached Saturn in November of 1980. It gave us new views of the rings, of the shepherd moons, of the hazy orange haze of Titan. It confirmed Titan's thick atmosphere and prompted the Cassini mission that would follow 2 decades later. And then, it kept going. Because Voyager 1 had been launched on a trajectory that after Saturn would take it out of the plane of the planets and outward into the interstellar medium. It had no more planets to visit. It had done its job, but the spacecraft was still healthy, and its instruments were still working, and so the mission continued, not to explore new worlds, but to explore the space between them. And for decades, Voyager 1 traveled, onward, outward, through the region where the sun's solar wind carves out a bubble called the heliosphere. The heliosphere extends outward to more than 100 astronomical units from the sun. It is shaped by the constant outflow of charged particles from the sun, and by the interstellar gas and dust that presses in from outside. On the 25th of August, 2012, Voyager 1 crossed a boundary called the heliopause. The heliopause is the place where the sun's outward pressure exactly balances the inward pressure of the interstellar medium. It is a frontier, a border, And Voyager One became on that day the first human-built object to cross it. The crossing was not a visible event. No boundary line flashed. No dramatic transition was photographed. But Voyager One's instruments registered a change. The density of cold plasma around the spacecraft increased. The character of the magnetic field altered. The charged particle fluxes shifted. The ambient environment had transitioned from the local flow of solar material to the interstellar flow of galactic material. We had, as a species, sensed something beyond the sun's bubble. Beyond the place where our star's breath can still be felt as a pressure. Into the quiet between stars.
And yet, and this is the part that is both humbling and astonishing, Voyager One had not yet reached the Oort Cloud, not even its inner edge. The heliopause lies at roughly 120 astronomical units. The inner Oort Cloud, depending on the definition, begins at 1,000 to 2,000 astronomical units. That means that when Voyager One crossed into interstellar space, it was still, at minimum, 10 times closer to the Sun than the nearest region where Oort Cloud bodies are thought to live. As of this moment, Voyager One is more than 160 astronomical units from the Sun. It is still in the local interstellar medium.
It is still in touch with Earth, through radio signals that take nearly a full day to travel the distance in each direction. Its power source is slowly fading. Its instruments are being shut down, one by one, to conserve electricity. Within the next decade or two, it will fall silent, not because it has crashed, not because it has failed, simply because its plutonium source will no longer provide enough power to operate even its most essential equipment. When it falls silent, it will continue to travel, onward, outward. Its velocity is about 17 kilometers per second relative to the Sun. Not a fast speed by the standards of the universe, but a relentless one. It does not slow. It does not stop.
It continues through the dark, a silent metal envelope from a civilization that, even then, may no longer exist in the form that built it. And here is where the scale of the Oort Cloud becomes a meditation. At 17 kilometers per second, Voyager One would take about 300 years to reach the inner edge of the Oort Cloud. 300 years. Many generations. By the time Voyager One arrives at that inner boundary, every human alive today will have died. Every person they ever met. Every language in which the Voyager mission is currently documented. The Voyager spacecraft will outlive us all and arrive at the edge of the Oort Cloud as a silent relic of a vanished age. And then it will enter the cloud itself.
But even within the cloud, even surrounded by trillions of icy bodies, Voyager One will encounter nothing. The density is too low. The distances between bodies are too great. The odds of Voyager One actually hitting one of them, or even passing close enough to one to register its presence, are vanishingly small. Voyager will drift through the Oort Cloud for tens of thousands of years, surrounded on all sides by the frozen wanderers, and encounter none of them. It will see nothing. It will be seen by nothing. It will simply pass through. To cross the outer edge of the Oort Cloud at 100,000 astronomical units, Voyager One would take approximately 30,000 years. 300 centuries.
30,000 years ago, humans had just begun to paint on the walls of caves. We were still in the late Stone Age. Agriculture had not yet been invented. Speech, we assume, was fully modern, but writing had not been conceived. 30,000 years is, in cultural time, a yawning gap, an epoch, And that is how long Voyager One will take, simply to cross the shell that surrounds our sun. When Voyager One finally leaves the Oort Cloud, if it is still recognizable, if it has not been shredded by some interstellar dust, if it has not struck a rare bit of debris, it will drift into the true space between the stars. It will become formally a free-floating interstellar object, no longer gravitationally bound to our sun.
Traveling toward the constellation Ophiuchus. Over the next 40,000 years, it will pass by a star called Ross 248, at a distance of about 1.6 light-years. And after that, other stars, over cosmic timescales. And all the while, the golden record will be aboard a silent spacecraft, drifting through the silence, carrying greetings and music that no one will ever hear, unless, in the vast span of time ahead, some improbable intelligence intercepts it and plays it. This is the long farewell. This is what it means to have sent something beyond our reach. We did not send it to do anything.
And because sending it was, in some strange way, an act of affirmation, an act that said, "We are here," or rather, "We were here."
Let me linger on these numbers. 300 years to reach the inner edge of the Oort Cloud, 30,000 years to cross it. These are not just statistics, they are meditations. They are the scale of the frontier, made concrete. 300 years from now is the year 2326. Imagine, if you can, what the world will look like then. If civilization persists, if humans remain on Earth, if the Internet and its successors still connect minds across continents, what will they be discussing? What dreams will they have? What planets will they have visited? What will they call themselves?
By the time Voyager One enters the Oort Cloud, if we have not destroyed ourselves or been destroyed by other forces, we will almost certainly have already sent faster probes to that region. Our current propulsion technologies are limited by chemical rockets, which are enormously inefficient. Future technologies, whether solar sails, ion drives, fusion, or something we have not yet imagined, will likely allow us to reach the Oort Cloud in decades, not centuries. Voyager One, by that time, will be a historical curiosity, a slow old envelope trailing behind the faster probes that overtook it. But that is only if progress continues along its current trajectory. There are futures in which it does not. There are futures in which civilization retreats, or fragments, or forgets.
There are futures in which the Oort Cloud remains, for humans, permanently unreachable. There are futures in which Voyager One remains our only emissary to the shell, simply because we never build another. 30,000 years is longer still. 30,000 years ago, the last Neanderthals were still walking the earth. Their cousins, the Homo sapiens, were beginning their long expansion across Eurasia. No written history exists from that time. We reconstruct what little we know from bones, stone tools, and cave paintings. An entire epoch of human existence, reconstructed from traces. 30,000 years from now is
similarly unimaginable. If our species survives, if we are still recognizable as human, what will we have become? By that time, genetic engineering,
artificial intelligence, if it is developed, will have reshaped our civilizations. Interstellar travel, if it is achieved, may have sent some of us to other stars. The very idea of being human may have been stretched, transformed, or replaced. And all of this unfolding of futures is the time it takes for Voyager One to cross a single region of our solar system. The Oort Cloud is not a place. It is a span of time as much as space. To contemplate the Oort Cloud is to contemplate time in ways that are rarely asked of us. It is to look at a structure so vast that its crossing is measured in cultural epochs, not in human lives.
It is to accept, with some humility, that our impatience is misplaced when it encounters this scale. The Oort Cloud does not care about our schedules. It does not reward our eagerness. It will release its bodies one at a time across hundreds of thousands of years, regardless of what we, in our brief historical flicker, have to say about it. And this, I think, is part of why the Oort Cloud is restful, why it calms us when we hold it in our minds, because it dwarfs our worries. It dwarfs our ambitions. It dwarfs even the tragedies and triumphs of our species, not in a mean way, not in a way that says we are unimportant, but in a way that offers perspective.
It says, whatever you are carrying tonight, the Oort Cloud was here before it, and will be here long after it. Your troubles, set against that backdrop, are small and temporary. Let them be small. Let them be temporary. Let them drift. And if Voyager One, with its golden record, and its aluminum hull, and its plutonium heart, takes 30,000 years to cross a shell of silent ice, then your life, with all its worries and joys, is not diminished by the comparison. It is contextualized. It is placed, like a small warm light, inside a much larger room. The room does not threaten the light. The room holds it. That is the gift of the Oort Cloud, not the numbers, not the orbital mechanics.
Not even Planet 9 if it exists. The gift is the scale itself, the scale that holds us, the scale that outlives us, the scale that asks nothing of us, and therefore frees us, briefly from the pressure of needing to be anything in particular. There will be a time, in the distant future, when Voyager One will cross the outer edge of the Oort Cloud. It will pass through and drift into true interstellar space. It will carry still the disk that was pressed onto it in 1977. It will carry a recording of the Brandenburg Concertos, a recording of Chuck Berry, a recording of Bach, a recording of Senegalese percussion. It will carry greetings in Sumerian and Akkadian and modern English and Chinese and dozens of other languages. It will carry a diagram of the hydrogen atom. It will carry a map showing the location of our sun among nearby pulsars. And all of that will drift. It will drift through the cold. It will drift through the starlight. It will drift until, after many thousands of millennia, perhaps it either encounters an intelligence that plays the record or is absorbed into some other star's debris field, or becomes so weathered by cosmic rays that its disk can no longer be read. Or Most likely, it simply continues, unseen, unchanged in any meaningful way.
A tiny artifact of a tiny world, drifting in a silence so deep that its own silence becomes indistinguishable from the silence of the void itself. That is not a tragedy. It is not a failure. It is, in its own strange way, a perfect completion of the mission. To have sent something, to have sent it far enough that we can no longer track it, to have released it, knowing that its future is not ours to witness. To have said, "We were here," and then to have let the spacecraft carry the message forward without us.
Where does the solar system end? This is the question, finally, that the Oort Cloud forces us to answer. And the answer is not what you might expect. If you had asked an astronomer 100 years ago where the solar system ends, they might have said at the orbit of Neptune, or a few decades earlier at the orbit of Pluto. They would have meant that the outermost planet marks the boundary. Beyond that, they would have said, is empty space, interstellar medium, nothing of interest. This is wrong. It was understandable, given the knowledge of the time, but it was wrong. Today, we recognize several competing definitions of where the solar system ends. Each of them captures something real. Each of them is used in a different context.
And each of them draws a different line. The first definition is the gravitational boundary. This is the Hill sphere of the Sun, the region in which the Sun's gravity dominates over the gravity of the rest of the galaxy. For our Sun, the Hill sphere extends outward to roughly 100,000 astronomical units, or about 1.6 light-years. Beyond that, the Sun's gravitational pull on an object is weaker than the pull of the galaxy itself, and the object is no longer bound to our star. By this definition, the outer Oort cloud is, roughly, at the edge of the solar system. An object at the outer edge of the Oort cloud is on the brink of being lost to the galaxy.
The second definition is the heliosphere. This is the region where the Sun's solar wind is the dominant shaping force. It extends outward to roughly 120 astronomical units. Beyond that, interstellar particles and fields take over. By this definition, the heliopause is the edge, and we crossed it in 2012 with Voyager One. The third definition is the last planet. For a long time, this was Neptune at 30 astronomical units, or Pluto at 39 astronomical units on average, or, more recently, debates about Sedna and its sisters. By this definition, the solar system ends wherever the last known major body is. Each of these definitions captures something, but each of them is also incomplete.
And the deepest truth, I think, is that the solar system does not end in any sharp sense. It fades. It fades gradually, from the bright inner region, through the Kuiper belt, through the heliopause, through the inner Oort cloud, through the outer Oort cloud, and into the deep interstellar medium. Each of these transitions is meaningful, but none of them is a clean edge. And if we take the gravitational boundary, the 100,000 astronomical units, as our edge, then the solar system is nearly 2 light-years across. 2 light-years. The nearest star, Proxima Centauri, is only about 4¼ light-years away. This means that the sun...
Our solar system, in this sense, is a vast fuzzy sphere, and it overlaps, or nearly overlaps, with the similarly vast fuzzy sphere of our neighbor. In the night sky, the stars look like distant pinpricks, far removed from us. But if we could see gravity as a visible field, we would see the solar system and its nearest stellar neighbors as overlapping spheres, trading influence, occasionally passing close enough that their Oort clouds, if both exist, might briefly shake hands. And this is how it has always been. Throughout the history of the solar system, stars have passed near us, and their gravity has disturbed our Oort cloud, sending showers of comets into the inner system.
These stellar encounters are rare on human timescales, but common on solar system timescales. Every few 100,000 to 1,000,000 years, a star comes within a few light years of our sun. Some of those encounters over the 4.5 billion years of the sun's existence have been very close. Close enough, perhaps, to have stripped some of the outer Oort cloud away. Close enough to have sent great waves of comets into the inner system, potentially bombarding the Earth, potentially altering the course of life's history. There is a hypothesis that the extinction of the dinosaurs 66 million years ago was caused by a comet. The comet may have been sent inward by a stellar encounter that perturbed the Oort cloud.
If so, the very history of life on Earth, the history that led to our species, was shaped, in part, by the interactions between our sun's Oort cloud and the gravity of passing stars. This is the deep truth of the true edge. The edge of the solar system is not a line. It is a boundary that other stars touch. The Oort cloud is where we meet our neighbors, gravitationally, over astronomical timescales. It is the diplomacy of stars. It is the silent conversation between solar systems, mediated by ice. And this is also why the Oort cloud is not merely a feature of our solar system. It is a feature of the galaxy. Every star has, we now believe, its own Oort cloud, or something like one.
Every star, in the course of its formation, has flung some debris outward into a spherical reservoir. The galaxy, on the scale of stars, is dotted with these cloud-held solar systems, each of them surrounded by its own shell of frozen ancient matter. When we study our own Oort cloud, we are studying a structure that is common, perhaps universal, in the galaxy. We are studying a feature of all stellar systems. We are studying in some sense the very texture of the interstellar medium at the scale where stars and their debris interact. And perhaps, in some far future, we will send spacecraft to other stars, and we will find, at the outer edges of those stars, their own frozen shells.
And our spacecraft will pass through them, as Voyager will pass through ours. Slow, silent, unaltered, crossing the boundaries between one cold sphere and the next. There is a kind of poetry in this picture. A galaxy made of stars, each surrounded by a shell of ancient ice, each shell occasionally brushing against its neighbors, each exchange leaving quiet ripples that, millions of years later, become comets in the sky of someone, somewhere, looking up at the night. We are not alone in the galaxy, not necessarily in the sense of other intelligences, though perhaps that too, but in the sense of other cold shells, other quiet frontiers, other worlds like ours, wrapped in their own Oort clouds,
waiting, silent, vast. And here, a final thought before we return home.
The Oort Cloud tells us something about the nature of boundaries themselves. In our daily lives, we are used to sharp boundaries. The wall of a room, the edge of a page, the coastline of a continent. These seem definite because at the scales we move through, they are. But on other scales, even these boundaries blur. A coastline, observed from the air, becomes a fractal edge, neither land nor sea, but a complicated interweaving of both. A wall, observed at the atomic scale, is mostly empty space with a sparse lattice of atoms. The apparent solidity of boundaries is a feature of how we perceive, not of what is truly there. The Oort Cloud teaches us this lesson on a cosmic scale.
The solar system, which from textbook diagrams appears to have a sharp outer edge, actually has no such edge. It fades, it blurs, it trades members with the galaxy. It is defined not by a line, but by a gradient. And that gradient, from the inner bright region, through the Kuiper belt, through the heliopause, through the inner and outer Oort clouds, into the interstellar medium, is the true shape of our home. It is a home without walls, a home whose furthest rooms are shared with the neighbors, a home whose boundaries are better described as transitions than as fences.
And perhaps, when we sit with this image long enough, we come to feel that our own lives, our own identities, our own places in the world might share this quality. That we too are gradients rather than sharp edges. That we too trade members with our surroundings, slowly, continuously, over time. That we too are defined less by our walls than by our transitions.
We come, now, to the end of our drift. Or perhaps not the end, because the Oort Cloud has no end in the sense that stories have endings. It simply continues. It simply is. And so this chapter is not a conclusion. It is a gentle return, a quiet lowering back into the night where you began. You have traveled tonight, with me, from the inner solar system through the Kuiper belt, past the heliopause into the inner Oort Cloud, among the orbits of Sedna and Leikuhonua, through the speculative presence of Planet 9, out to the outer Oort Cloud, and finally to the gravitational edge of our sun's reach, where the galaxy begins to touch us, and we begin to touch the galaxy.
You have met 1 trillion silent bodies, drifting in a shell that surrounds everything you have ever known. You have met a Dutch astronomer working in a quiet room in 1950, reasoning this shell into being from nothing more than the mathematics of comet arrivals. You have met Michael Brown and Konstantin Batygin, searching for a 9th planet whose gravity may or may not be there. You have met Voyager One, a golden envelope from a civilization that may or may not persist, drifting outward into an emptiness so vast that its crossing is measured in cultural epochs. And now, as we return, I want to leave you with a final thought. Because the Oort Cloud is not just a scientific object, it is a mirror.
The Oort Cloud is what our solar system looks like when it is at rest, when the warm, bright, busy inner regions are stripped away, when the spinning planets, with their oceans and clouds and storms, are set aside, when the asteroid belts, with their collisions and fragments, are quieted. What remains is the Oort Cloud. A vast, spherical population of ancient, frozen bodies, almost entirely motionless on human timescales.
And when we close our eyes tonight and try to imagine our home in the galaxy, we should not picture only the 8 bright planets. We should picture the full structure, the sun in the middle, the inner planets nearby, the belt of asteroids, the 4 giants, the Kuiper belt, the heliopause, and then reaching outward in every direction, the vast sphere of ice, the silent shell, the trillion quiet wanderers that make up the true bulk of our solar system's population. That is our home. That is where we live. Not on a small blue world alone, but inside an immense spherical library of frozen ancient matter, with a small blue world at its heart. And it is beautiful.
Not beautiful in the way that a sunset is beautiful, or a flower or a human face, but beautiful in the way that silence is beautiful, in the way that deep water is beautiful, in the way that old stone is beautiful. Beautiful because it is ancient and vast, and it does not care about us, and precisely because it does not care, it holds us. You are right now inside this holding. You are on a small, warm world, inside a fuzzy sphere, nearly 2 light years across, surrounded by 1 trillion bodies of ice that have been there for 4.5 billion years, and will be there for 4.5 billion more. The cloud does not move on your timescale. It does not change.
It simply is. And when you sleep tonight, the cloud will be there. When you wake tomorrow, the cloud will be there. When you live your whole life, from whatever age you are now until whatever age you reach, the cloud will be there, unchanged. And when you are gone, when your descendants are gone, when your civilization is gone, when your species is gone, when the sun itself eventually ages and swells and becomes a red giant and then a white dwarf, the cloud will still be there. Its bodies will drift slowly, perturbed by the dying sun's changes, scattered gradually by the galaxy's tides.
Over tens of billions of years it will dissolve, its members joining the interstellar medium, their frozen gases slowly warming as they wander among other stars. But on any timescale that we can imagine, on any timescale that human concerns can measure, the cloud is permanent. It is the quietest part of our solar system, and perhaps, for that reason, the most honest. Because the planets, in their warmth and motion, are always doing things. They are weathering, they are erupting, they are orbiting, they are, in a sense, always in motion. But the Oort Cloud simply is. It abides. It waits. It holds. And it does not need us to know about it. It does not need us to map it.
It does not need us to send probes or to name its members or to write papers about it. It was there before we noticed it, and it will be there long after we forget it. Our attention or inattention does not change it. There is something deeply peaceful about this, something that, I hope, has settled into you as you have drifted with me through these chapters, through these facts, through these reflections. The Oort Cloud is not a place you can visit, but it is a place you can hold in your mind. And when you hold it, you are held in turn.
Because to think about something so vast, so old, so patient, is to briefly step outside your own temporary worries and to feel, if only for a moment, what it is to belong to something much larger than any single life. You belong to this. You belong to a solar system whose outer shell is nearly 2 light-years across. You belong to a population of 1 trillion frozen bodies that drift in silence at the edge of your home. You belong to a galaxy in which every star has its own such shell, and in which the ancient ices of countless solar systems quietly trade in the space between. You belong to something old and cold and beautiful. Let that belonging settle into you. Let it replace, briefly, the smaller belongings that have been pressing on your mind. The deadlines, the worries, the half-finished thoughts. Set them gently aside. The Oort Cloud does not need you to solve them tonight. And as you breathe, as you rest, as you let this hour become whatever it wants to become, know that the cloud is there, silent, vast, ancient, faithfully drifting at the outer edge of our sun's reach. Trillions of small frozen worlds, each on its own slow path, each accompanied by nothing, each quiet. And somewhere among them, perhaps, a hidden planet. A world we have not yet found. A world that has been there since before us, and will be there long after. That is the Oort Cloud.
That is where our story ends for tonight. Not with a moment of climax, not with a dramatic finale, but with a slow, gentle return. A return to your own breath. A return to your own body. A return to the small, warm place on the small, warm world where you happen to be right now. The cloud holds the world holds the room holds you. And somewhere out there, at the true edge of the sun's reach, a small icy body is completing another quiet arc around its ancient star. It has been doing so for 4.5 billion years. It will continue. It will not know that we existed. It will not know that we looked outward.
It will simply continue. And perhaps in its slow, patient drift, it offers us the gentlest lesson of all. That the greatest things in our solar system are not the bright, the loud, the fast. They are the quiet, the cold, the patient. The shell that surrounds us, drifting through the galactic night, asking for nothing, holding everything. Sleep now, or drift, or simply be still. The cloud is there. You are here, and that is, for this moment, enough. Total, 17,081 words, 12 chapters.